Page 389, section 6.3 is volume by cylindrical shells. Remember we said that there are two different methods for finding the volume of one of these figures. The method of 6.2 is what AP requires. So, okay, then why are we learning a second method for this? Why are we learning section 6.3 if AP doesn't require us to do it? Here's the deal. Let's say that you take what we've got here in example number 1. They asked me, take the region y is equal to 2x squared minus x cubed, and y is equal to 0, which is, of course, the x-axis. So that would be this region right here. And they asked me to revolve it around the y-axis and find the volume of that resulting figure. Here's the problem. By method 6.2, when I'm revolving around the y-axis, everything has to be in terms of y, right? So that means that I would have to solve this equation for x to get it in terms of y. That just doesn't look like a whole lot of fun to me. And it's going to create an obnoxious equation that I'm then going to have to work with, right? It would be so nice if I was in control. If whatever equation they gave me, I had the ability to look at it and go, you know, I'd rather leave that as it is in terms of x instead of having to solve it for x and put it in terms of y. So that's what method 6.3 is going to give me the ability to do, because you'll notice that by the method of section 6.3, if I'm revolving around the y-axis or a vertical axis, instead of everything being in terms of y, everything is going to be in terms of x. And the same thing is going to hold true when I revolve around an x-axis or a horizontal axis. Everything is going to be in terms of y. So that'll give me the flexibility of no matter what I'm revolving around, I can look at the equation and decide for myself which is easier to work with, terms of x or terms of y, and I'll have a method that'll help me do that. So for the AP exam, on the multiple choice, they are going to give you problems where they just have you give the setup. They'll set it up by 6.2. But then they'll also give you multiple choice and they'll give you FRQs where you're to come up with the solution, and they will take either method for coming up with the solution because it'll lead you to the same answer. Okay? So we're just giving ourselves an extra tool here that will make our work a little bit simpler. So now that we understand the purpose of this section, let's talk about what cylindrical shells, what they mean by that. All right, so we've got this figure up here, f of x, and they ask us to take the area underneath that curve and to revolve it around the y-axis and find the volume of that figure. Okay? What we typically would do is we would do horizontal cross sections, right? And that would give us like a disc or a donut. Instead, what we want to do is we want to do a vertical cross section. And so when I do that vertical cross section and I spin it around, I'm going to create something like a koozie. You know, koozie, those things that you put around your Coke can. That's what we're talking about. It's kind of, that's the type of figure that we're looking at around your Coke can. Yes. So, if you were to take several different size koozies and set them inside each other, that's like the figure that we see over here. It's like they're nested inside of each other. So here's one cross section that got revolved around and made a koozie, and here's another cross section that got revolved around and made a koozie, and here's another one and another one. So I could find the volume of one of those koozies, and then I could do the summation from the first one to the last one, right? Okay, so how do I find the volume of one of those? Well, if I slice this open and I unroll it, it's literally just a rectangle, right? So if I'm trying to find the area, area is going to be length times width. So let's think about the length for a second. That length came from unrolling this. It's just the circumference, right? So circumference is going to be 2 pi r. So we can come down here and say this length is going to be 2 pi r. Now you'll notice that if I'm looking for the radius, I'm just starting at 0 and going straight across horizontally. That's going to be the same thing as my x value then. And so you'll see that they're telling us radius and x are the same thing, so they'll actually go ahead and write this as 2 pi x down here instead of 2 pi r. Then I also need the height of my figure, or the, if you think of it as length times width, the width of my figure, however you want to think of it. So if I'm looking for that width right there, or that height, I'm going to have to say the top function minus the bottom function. Sounds familiar, right? So in this case, it would be f of x minus the x-axis, which is 0. So it would just be f of x minus 0. So we could say that this dimension is f of x. So if I want the area, it's going to be 2xh times f of x. 2xh times f of x, where x is representing the radius and f of x is representing that height. So then the third dimension that I would need for volume is just the thickness of this. And as we've seen before, we can represent that thickness with the change in x and think of it like a dx. So we could think of this as the volume of one koozie, and then we would want the summation starting here of each of these koozies that are created from the cross sections. So I would want the summation from A to B. Okay, so that's the idea behind cylindrical shells. Now, as we've already alluded to, when you're revolving around a y-axis or a vertical axis, everything is going to be in terms of x. But here is a constant in both sections 6.2 and 6.3. The radius is always perpendicular to the axis that you're revolving around, no matter what section you're in. So that's something that we can kind of use as a foundation to hold on to. If my radius is perpendicular, that means my height's going to have to be parallel, right? So that would be something else that will help us here. And then we also have a little bit of a shortcut down here. Like we saw up here a second ago, we were revolving around the y-axis, x equals 0, and so our radius ended up just being our x value. And so that's what they tell me. Anytime you're revolving around x equals 0, your radius will just flat be your x value. So let's look at example number 1. For example number 1, it says find the volume of the solid obtained by rotating about the y-axis the region bounded by y equals 2x squared minus x cubed and y equals 0. All right, so here's y equals 2x squared minus x cubed, and here's y equals 0. So we want to take this region in here and we want to revolve that around the y-axis. So I'm going to cut a cross section, and remember that my height is going to be parallel to what I'm revolving around. So let's find our height over here. Our height is just going to come from top minus bottom. So the top equation was 2x squared minus x cubed. The bottom equation was 0. So my height is just going to be 2x squared minus x cubed. So we can go ahead and put that in over here for f of x. All right, then our radius is perpendicular to the axis we're revolving around. So again, we're revolving around the y-axis, so the radius would be perpendicular to that. That means start at 0 and go straight across. That's just going to be our x value. And again, they told us that shortcut that our radius would be our x value in this case. But we can see it with logic as well. All right, so then I can go through and say, hey, I cut a cross section here, but I would also want one here and here and here and here and here and here. So even though this has already pretty well laid itself out that I'm using only x values, we can also see that for a and b, we would want to be using the x values. Now, remember where we get those upper and lower limits of integration? They come from taking the two equations and setting them equal to each other and solving. So in this case, our two equations were 2x squared minus x cubed and 0. We set those equal to each other and solved, and we got 0 and 2. So that's where those come from. It's the points of intersection. Also remember that if it helps you to see an image something like this, use one of those free online 3D graphing software emulators, and that might make it a little easier for you to envision what you're working with as well. All right, let's look at another one of those. Example number 2. Example number 2 says find the volume of the solid obtained by rotating about the y-axis the region between y equals x and y equals x squared. All right, so here's y equals x and here's y equals x squared. So it's this little blue region here, and again we're revolving around the y-axis. All right, so we know that our radius is going to be perpendicular to what we're revolving around. So if we're revolving around y, our radius is going to be this way. Again, it's starting at 0 and going straight across, so it would just be our x value, and we do have that given shortcut that when we're revolving around the y-axis, our radius is always x. Our height then is going to be parallel to the axis we're revolving around. So for this height, we're going to do top minus bottom. So what equation is on the top? Y equals X, right. So for top, I'm going to do X, and then for bottom, the bottom equation was the parabola Y equals X squared. So when I do top minus bottom to get my height, I'm going to get X minus X squared. And again, it has already laid itself out in terms of X without us even having to memorize that it was in terms of X. But that also shows us that when we come over here and we say, okay, I've already done one cross section here, but I would want one here and here and here and here and here. Again, we're moving along the x-axis, so we're going using those x values of 0 and 1. And the way that we find those starting and stopping points, again, they are from setting the two equations equal to each other and finding the points of intersection. Same thing that we've been doing since section 6.1, right? When we were doing area. So 6.1, 6.2, and 6.3, we're doing that same thing. All right, example 3. For example number 3, they ask me to revolve around the x-axis. So let's talk about that. If I'm revolving around the x-axis or any horizontal axis, I'm going to have everything in terms of y. My radius is still perpendicular to the axis I'm revolving around. And I also get a shortcut with this one that when I'm revolving around the x-axis where y equals 0, then my radius is just going to be y. And my height is still parallel to the axis that I'm revolving around. Okay? So for example 3, it says, use cylindrical shells to find the volume of the solid obtained by rotating about the x-axis, the region under the curve y is equal to the square root of x from 0 to 1. All right, so here's y is equal to the square root of x. You could also think of that as x equals y squared if you solved it for x. So whichever way you want to think about it, here's x equals y squared. And they told me to go from 0 to 1. So it would just be this blue region right here. And I want to spin that around the x-axis. So when I do, I'm going to create a figure similar to this. My radius is going to be perpendicular to what I'm revolving around. And so for my radius, if I start here and I go straight up perpendicular to that x-axis, you can see if I start at 0 and go straight up, that's just a y value. And sure enough, that's my shortcut, that when I'm revolving around the x-axis, my radius will just be y. My height is parallel to what I'm revolving around. So since I'm revolving around the x-axis, I'm going to choose a cross-section parallel. And so I'm going to need to do right minus left. So my right equation is 1, and my left equation is y squared. So my height's going to be 1 minus y squared. And again, without us really doing it by the memorized fact, we were using common sense again, but you'll notice this has laid it out so that we're only using y values, and it should be in terms of y. So that tells me that for my upper and lower limits of integration, I want my y values as well. So I'm going to go from 0 to 1. All right, so just as we did the first night on 6.2, we just want to do a couple of these for 6.3 so that we have time to really study the section, look back over the examples, and really process this and make sure that we can do a couple of them well. And then the second night we can work on changing the axis of revolution and doing some extra problems. So for tonight on pages 392 to 393, we're doing 3, 5, 9, 11, challenge 19.